The human body has a lot of protons, and when these protons are subjected to an external magnetic field, they align with that field. Now, when we send a radio frequency current through the body, these protons spin out of equilibrium, and after the current is turned off, they realign with the magnetic field. But in different tissues of the human body, the rate of realignment is different. Using that, we can produce images of various parts of the human body and study them. And that is how an MRI machine works, using the concept of nuclear magnetic resonance. What's that? Let me explain. In nuclear magnetic resonance, protons or atoms with odd number of protons or neutrons can either align in the direction of an external magnetic field or align opposite to it, known as the alpha and beta spins respectively. We can observe that alpha spin is the lower energy state and beta spin is the higher energy state because, obviously, it is easier to swim downstream than upstream, right? It's also important to understand that if an atom is more surrounded by electrons or if it is shielded, the energy difference between the alpha and beta spins is smaller when compared to an atom that is less surrounded by electrons or, in other words, deshielded. Studying the energy difference between alpha and beta spins is very useful. For instance, let's take two molecules A and B, one fluoropropane and two fluoropropane. Fluorine's electronegativity allows it to pull electrons towards itself, so the hydrogens closer to fluorine will be less shielded and the ones further away will be more shielded. So, the NMR spectrometer will show 3 different readings for molecule A, because 3 different sets of hydrogens are progressively distant from the fluorine atom, and it will show 2 different readings for molecule B due to its symmetric structure. This is one of the many uses of NMR in chemistry. While it is useful with a large number of atoms, controlling a single atom becomes difficult with NMR. It's like trying to move a particular ball on a billiards table and lifting and shaking the whole table. We will move the intended ball, but the other balls get moved too. The solution to this is nuclear electric resonance. Unlike magnetic fields, electric fields are highly localized. They can distort atomic bonds around the nucleus, causing it to reorient itself. So what's the big deal with nuclear resonance? Well, I'll have you know that in today's world, NMR already has numerous applications in various fields like medicine, mining, organic chemistry, and many more. Although nuclear electric resonance is still in its development stages, it has a lot of potential for the future. It will play an important role in the field of quantum computing. Further research in NER will also enable us to better understand the boundaries between the classical and quantum realms of physics.